From colossal construction sites to molten steel, this story reveals how modern infrastructure is forged through precision, power, and vision. The Shuangbaoguan Bridge is a remarkable feat of modern bridge engineering located in Chongqing, China, spanning the deep gorges of the Dedong and Xiaodongge rivers. This dual continuous arch bridge is recognized as the world's largest double-span continuous arch structure. Rising approximately 320 meters from the bridge deck to the bottom of the gorge, it ranks among the highest bridges on Earth and has been honored with the prestigious Lindenthal Medal for Engineering Excellence. As the core structure of the S549 Shuangbao-Longhua underpass reconstruction project in Jiangjin District, the bridge plays a vital role in the Yanjiang Highway Network. Constructed by China State Construction Engineering's 6th Engineering Bureau, the bridge has a total length of 620 meters, featuring two impressive main arch spans of 405 meters each. It carries an expressway that significantly improves connectivity between Shuangbao District and Longhua Town. Nearby, the slender Dedongge iron cable bridge, built to transport construction materials, has also gained widespread attention on social media for its striking, paper-thin appearance high above the gorge. The steel bar manufacturing process starts with the collection, sorting, and preparation of scrap steel and iron materials. These raw materials are carefully inspected to remove contaminants before being charged into an electric arc furnace. Inside the furnace, powerful electric arcs generate extremely high temperatures, melting the metal into a liquid state. During this stage, slag forms on the surface and is removed to eliminate unwanted impurities. Alloying elements are added to precisely control the chemical composition and ensure the required mechanical properties of the steel. Once refining is complete, the molten steel is tapped from the furnace into a ladle. The liquid steel is then transferred to the continuous casting system, where it is poured into water-cooled copper molds. As the steel moves through the molds, it gradually solidifies into long, solid billets with a uniform cross-section. Secondary cooling sprays further reduce the temperature, and the billets are cut to specific lengths using automated cutting equipment. The solid billets are then transported to a reheating furnace. In this furnace, they are heated evenly to the optimal rolling temperature, ensuring sufficient plasticity for shaping. After reheating, the billets enter the rolling mill line, where they pass through a sequence of roughing, intermediate, and finishing stands. Each set of rollers progressively reduces the billet's cross-sectional area while elongating it into steel bars of the required diameter. Surface ribs are formed during the rolling process to enhance bonding strength in reinforced concrete applications. Following rolling, the hot steel bars are transferred onto cooling beds. Here they are cooled under controlled conditions to achieve the desired balance of strength, hardness, and ductility. Uniform cooling also helps prevent internal stresses and deformation. After cooling, the bars pass through straightening machines to correct any bends or distortions. In the final stage, the straightened steel bars are cut to standard commercial lengths. They are then bundled, securely tied, and labeled according to size and grade. The finished products are prepared for storage and transportation, completing the steel bar production process. The hot rolling process begins when steel billets are heated in a reheating furnace until they reach the required rolling temperature. Once uniformly heated, each billet exits the furnace and is transferred to the rolling line. The existing 14 mill stands, arranged in a tree configuration, now function as the roughing and intermediate mill. In these stages, the billet is progressively reduced in cross-section and elongated, forming a rough round bar while maintaining stable material flow. Throughout rolling, the workpiece is cropped several times at both the leading and trailing ends. This repeated cropping removes defects and ensures consistent quality along the entire length of the bar. After roughing and intermediate deformation, the already rounded bar enters the finishing section, which is equipped with a new 5-stand precision sizing mill with 3-roll technology. In each PSM stand, 3 rolls completely surround the workpiece. This configuration produces an optimal round cross-section and minimizes ovality. Each stand is driven individually, allowing precise control of rolling speed and force. A key feature of the PSM is the hydraulic adjustment of the rolls under load. The roll gap can be adjusted within milliseconds during rolling, enabling exact diameter control even when temperature or material conditions change. The PSM is dedicated to rolling special bar quality steels in final diameters ranging from 25 to 83 millimeters. Diameter tolerances achieved in this process are 6 to 10 times tighter than standard requirements and remain consistent along the full bar length. Rolling can also be performed in free size mode, allowing any required intermediate dimension to be produced. This capability helps minimize machining allowances for downstream processes such as peeling. The entire rolling operation is fully automated and monitored by the technological control system. The system controls hydraulic roll adjustments, monitors process parameters in real time, and integrates existing measuring equipment. Operators can observe and manage all key data through a clearly structured user interface. When a size change or roll replacement is required, prepared PSM stands are delivered from the roll workshop to the mill. The automated stand changing process includes pushing out worn stands, pushing in new ones, and automatically coupling drives, media, and power supplies. Smaller size changes do not require replacing all 5 stands, reducing downtime. Once the stand positions are confirmed, the automation system is already preset, allowing production to resume immediately at high speed. After final sizing in the PSM, the hot-rolled bars are cut to customer-specified lengths. The finished products are then transferred onto a RICE-type cooling bed, where controlled cooling stabilizes the material properties before further handling and delivery. When the partially solidified strand exits the mold, it enters the strand guide system consisting of 8 precisely aligned segments. This system supports the strand, maintains its geometry, and guides it smoothly along the casting arc. At this stage, secondary cooling is applied through an integrated air mist cooling system. By using a controlled mixture of air and water, the system achieves uniform heat extraction, ensuring stable cooling rates and preventing surface or internal defects. This controlled cooling promotes high steel cleanliness and the formation of a homogeneous internal microstructure throughout the slab. During continuous casting, the solidification process is closely monitored and regulated by advanced technological control systems. Process models such as dynamic solidification control and dynamic soft reduction are applied to compensate for shrinkage during final solidification. These functions reduce center segregation and internal porosity, resulting in slabs with improved density and consistent mechanical properties. Continuous mold and strand monitoring allows real-time adjustments to casting parameters, ensuring stable operation throughout the sequence. After the strand has fully solidified, it is cut to the required lengths. A primary torch cutter performs the initial cutting of the continuously cast strand, while a secondary torch cutter ensures precise final slab dimensions. This two-stage cutting process guarantees accurate length control and smooth slab edges. The finished slabs are then lifted and transported by overhead crane for further handling and transfer to the rolling mill. Throughout the entire casting sequence, automated systems coordinate and supervise each step, ensuring reliable operation, high productivity, and consistently high slab quality. A magnetic separator installed on a conveyor belt is an essential piece of equipment widely used in modern industrial processing. Its primary function is to automatically separate unwanted ferrous materials, such as iron particles, steel fragments, or metal contaminants, from bulk materials as they move along the conveyor system. In operation, mixed raw material is continuously fed onto the conveyor belt, which acts as a carrier for transportation. Positioned either above or within the middle section of the belt is a powerful magnetic unit. As the material passes beneath this magnetic zone, ferrous impurities are attracted by the magnetic field and lifted away from the main material flow. Meanwhile, non-magnetic materials continue moving forward uninterrupted toward the next stage of processing. Magnetic separators can be designed using permanent magnets or electromagnets, depending on the application and separation requirements. Electromagnetic separators offer adjustable magnetic strength, making them suitable for handling heavier or more deeply embedded metal contaminants. These systems are engineered to operate at high belt speeds while maintaining reliable separation efficiency. This type of separator plays a crucial role in industries such as mining, recycling, cement production, food processing, and material handling. By removing metallic impurities, the system helps protect downstream equipment like crushers, mills, and mixers from damage, reduces maintenance costs, and improves overall product quality. In addition, magnetic separators enhance workplace safety by preventing metal fragments from entering sensitive machinery. Their simple integration into conveyor lines, continuous operation, and low maintenance requirements make them a practical and cost-effective solution for industrial material separation. The pipe installation process begins with a daily visual inspection of all lifting equipment. Any damaged or worn slings, hooks, or hardware must be replaced before work proceeds. Prior to excavating the trench, an embankment may be constructed, rising at least 4 feet above the top of the pipe or up to the subgrade elevation. Once excavation is complete, the trench bottom is compacted and proof-rolled using approved self-propelled trench compactors to ensure adequate bearing capacity. A proper bedding layer is then prepared. For concrete pipes, A 6-inch bedding layer made of AASHTO number 8 aggregate is placed, while metal and thermoplastic pipes use PIN.dot number 2A aggregate. This bedding material is leveled but not compacted. Pipes are lowered carefully into position, with bells or grooves facing upgrade and spigot ends fully inserted into the hubs. If lift holes are present, they are sealed with soil-tight manufactured plugs. Pipe alignment and grade are controlled using string lines, laser systems, or other approved methods, maintaining a minimum slope of 0.35%. On straight alignments, pipe joints are completed around the full circumference, excess caulking is removed from the interior, and the exterior joints are sealed. Metal pipes are connected using bands at least 12 inches wide, ensuring dimples do not index into each corrugation. Thermoplastic pipes use preformed gaskets installed according to the manufacturer's instructions, often with 2 layers of Class 1 geotextile. Backfilling begins along the sides of the pipe using coarse aggregate placed in 4-inch compacted lifts. Hand-operated jumping jacks or vibratory plate compactors are used until visual non-movement is achieved. Proper lateral compaction is critical, as much of the pipe's load-bearing strength comes from side support. Trench backfill requirements specify coarse aggregate under roadways, shoulders, and in embankments where the pipe crown is within 4 feet of subgrade. Finally, backfill above the pipe is placed in controlled lifts, 4 inches when using smaller compactors, or up to 12 inches with excavator-mounted hydraulic plate compactors, following applicable roadway construction and pipe manufacturing standards. The Roddy R-8 pipe bursting system has earned recognition for its compact design, impressive pulling power, and versatile applications. To begin with, pipe bursting is a trenchless method used to replace old or damaged underground pipes with new ones of the same or larger diameter. Instead of excavating a continuous trench along the damaged pipeline, 2 compact excavations are created, a launch pit at the starting point and a receiving pit at the end of the pipeline section scheduled for replacement. These pits are sized only to accommodate the pipe bursting equipment, which helps preserve surrounding pavement, landscaping, and nearby structures. Once excavated, the pits are stabilized and leveled to provide a safe and accurate working environment. After the pits are completed, the damaged pipeline is inspected to confirm alignment and continuity. Any obstructions inside the old pipe are removed to allow smooth passage of the pulling cable. The pipe bursting system is then positioned inside the launch pit, ensuring that it is perfectly aligned with the existing pipe to avoid deviation during the bursting operation. Accurate alignment at this stage is critical, as it determines the straightness and final position of the replacement pipe.
Just want to pull it while he's in the hole. Get it started.
Next, the Roddy R-8 pipe bursting system is assembled. A bursting head, also known as an expander or bursting cone, is selected based on the diameter of the old pipe and the required diameter of the new pipeline. This bursting head is securely attached to the front end of the new continuous pipe, which is typically made of high-density polyethylene due to its flexibility, strength, and resistance to corrosion. The HDPE pipe is laid out above ground in a straight line behind the launch pit, fused into one continuous length to match the full replacement distance. A steel pulling cable or rod is then inserted through the old pipeline from the receiving pit toward the launch pit. Once the cable reaches the launch pit, it is connected to the bursting head. The opposite end of the cable is attached to the Rebar-8 hydraulic pulling unit, which is firmly anchored inside the receiving pit. The anchoring system is designed to resist the high pulling forces generated during the bursting operation and prevent any movement of the machine. With all mechanical connections secured, the hydraulic power unit is activated. This unit supplies controlled hydraulic pressure to the pulling system, allowing precise regulation of pulling speed and force. Before full operation begins, the system is tested under low load to confirm that the cable, bursting head, and new pipe are correctly aligned and functioning smoothly. Once testing is complete, the pipe bursting operation begins. The hydraulic unit steadily pulls the bursting head forward through the old pipe. As the bursting head advances, its expanding diameter applies radial pressure to the surrounding pipe walls. This pressure causes the existing pipe, whether made of clay, cast iron, concrete, or brittle plastic, to fracture along its length. The broken pipe fragments are forced outward into the surrounding soil, creating space for the new pipe. At the same time, the attached HDPE pipe is pulled directly behind the bursting head. This simultaneous bursting and replacement process ensures that the new pipe occupies the exact alignment and depth of the old pipeline. The soil displaced by the fractured pipe absorbs the debris without requiring removal, maintaining ground stability around the new installation. Throughout the operation, technicians closely monitor hydraulic pressure readings to ensure the pulling force remains within safe limits. Adjustments are made as needed to account for changes in soil conditions, pipe material resistance, or alignment. The controlled pulling action of the Rebar-8 system allows the bursting head to progress steadily, preventing sudden shocks that could damage the new pipe or surrounding infrastructure. As the bursting head moves forward, the new HDPE pipe slides smoothly into the underground cavity created by the fractured pipe. Due to its flexibility, the HDPE pipe can accommodate minor changes in alignment while maintaining structural integrity. This characteristic is especially important when replacing pipelines beneath roads, sidewalks, or buildings, where precise positioning is essential. When the bursting head reaches the receiving pit, the hydraulic pulling process is gradually slowed and then stopped. The bursting head emerges fully into the pit, completing the replacement of the old pipeline section. The pulling cable is disconnected, and the bursting head is detached from the new pipe. The newly installed HDPE pipe is then inspected to ensure it is properly seated and undamaged. Following installation, the ends of the new pipe are trimmed and prepared for connection to the existing pipeline network. Mechanical couplings, or fusion joints, are used to integrate the new pipe seamlessly with adjacent sections. These connections are checked for alignment and tightness to ensure a leak-free system. Once connections are completed, the launch and receiving pits are carefully backfilled, using appropriate materials to restore ground stability. Compaction is performed in layers to prevent future settlement. The surface is then restored to its original condition, whether it involves pavement, soil, or landscaping. The pipe bursting process using the RODI-R-8 system concludes with a functional check of the newly installed pipeline. By replacing the damaged pipe in place, this method achieves efficient rehabilitation while avoiding extensive excavation. The entire operation demonstrates a continuous, controlled sequence in which the old pipe is fractured, displaced into the surrounding soil, and immediately replaced by a new, durable pipeline in a single integrated process. Blakeman Steel, a family-owned company founded in 1988, is a leading structural steel erection and tilt wall specialist based in Fort Worth, Texas. Known for quality and dependability, the company has built lasting relationships with fabricators, contractors, and developers, completing projects nationwide. With over 200 years of combined management experience, Blakeman Steel brings expertise to every project, from warehouses and offices to schools, churches, industrial, and multi-story structures. Their skilled crews handle not only structural steel, but also stairs, canopies, mezzanines, railings, ladders, and ornamental work. Safety is a top priority, supported by thorough training and continuous certifications. Equipped with a fleet of cranes up to 250 tons, aerial lifts, forklifts, and trucks, Blakeman Steel is fully prepared to deliver reliable, safe, and high-quality results. The steel erection process begins with prefabricated structural members arriving on site, already cut to length, drilled, and clearly marked according to detailed shop drawings. Each steel component has a unique identification number that corresponds precisely to its designated position in the structure. This preparation allows the erection crew to work efficiently and accurately once lifting operations begin. A crane is the central piece of equipment used to handle the heavy steel members, some of which weigh as much as a large car. Operated with precise controls, the crane lifts columns, beams, and joists into place, while a spotter monitors all movements to ensure safety. Special attention is given to overhead high-voltage power lines, with strict clearance maintained at all times. No workers are permitted beneath suspended loads, and all movements are slow and deliberate to reduce risk. Steel columns are first lowered into preset anchors embedded in the existing concrete foundation. Workers guide the columns carefully so they align correctly in both north-south and east-west directions. Temporary bolts are installed to hold each column in position. Cross beams and floor beams are then lifted and connected between the columns. At this stage, most bolts are intentionally left loose to allow flexibility for alignment as additional members are added. Each crew member has a defined responsibility during erection. One worker verifies that every steel piece is placed in its correct location according to the drawings. Others focus on plumbing columns, checking levels, tightening bolts, or guiding loads as they are set. This coordination ensures the structure develops accurately as a whole, rather than as isolated parts. Once the primary frame is assembled, workers begin checking the entire structure for levelness and squareness. Using levels, measuring tools, and string lines, they confirm that all beams and columns are perfectly aligned and at right angles. This step is critical, as any misalignment in the steel skeleton would affect all subsequent construction stages, including elevator shafts, stairwells, and interior systems. After alignment is confirmed, bolts are tightened to their final torque, and permanent connections are secured through bolting and welding. Metal decking is then installed on the steel beams to form the base for floor slabs. Openings for elevator shafts and stairways are carefully maintained to exact dimensions to ensure proper operation later. Concrete is poured over the metal decking to complete each floor level. With the lower floors finished, the crew proceeds upward, repeating the same process of placing beams, checking alignment, installing decking, and securing connections on higher levels. Decorative and functional steel extensions are also installed as part of the frame. After several weeks of coordinated effort between skilled workers and heavy machinery, the steel frame is fully erected, leveled, and secured. The completed structure forms a rigid, precisely aligned skeleton, ready to support all remaining phases of construction. The VSM-057 E-Cage welding machine, developed by MBK Maschinenbau GmbH, is an advanced industrial solution designed for the high-speed and fully automated production of reinforcement cages. It is widely used in the manufacturing of cages for driven and board piles, structural columns, and concrete beams. As part of the VSM series, the machine applies modern coil technology, in which the welding unit rotates around a stationary cage, ensuring stable operation and consistent accuracy. One of the key strengths of the VSM-057E is its ability to produce versatile cage geometries, including round, triangular, square, and rectangular shapes. This flexibility is achieved through easily exchangeable index plates, allowing fast adaptation to different project requirements. The machine offers a high level of automation, enabling production to be monitored by a single operator. Longitudinal wires are automatically fed from standard coils, reducing material handling and storage needs. In addition, the VSM-057E delivers excellent welding quality thanks to electronic welding point control, which precisely regulates welding power, pressure, and pulse duration. User-friendly operation is ensured through a touch panel interface combined with an IPC PLC control system. For modern production environments, LAN and WLAN connectivity support remote diagnostics, software updates, and efficient production planning. Trick-track spacers are first positioned beneath the B1 reinforcement layer to ensure correct concrete cover and stable support. The B1 BAMTech carpet is then rolled out in the normal manner, running straight across the slab and directly over the column location where the positional couplers have already been cast into the column. Care is taken to maintain alignment as the carpet is unrolled and fixed in place. Once fully deployed, the B1 layer is checked and confirmed complete. Next, the B2 BAMTech carpet is rolled out perpendicular to the B1 layer, forming a 90-degree arrangement that creates the required orthogonal reinforcement grid. After the B2 layer is correctly positioned, work continues at the column connection points. The central collar of each positional coupler is carefully placed onto the bottom male half that is cast into the column, ensuring accurate engagement and alignment. Cranked reinforcement bars fitted with the second male half of the positional coupler are then installed, connecting securely to the central collar and transferring loads between the slab and the column. Following this, the prefabricated perimeter U-bar reinforcement is installed, running between the bottom and top reinforcement mats to provide edge restraint and continuity. Heavy-duty wire high chairs are then positioned across the reinforcement to maintain the design spacing between the lower and upper layers. Finally, the top BAMTech carpet mats are installed. Cranked terminating column bars are placed between the bottom and top mats, completing the reinforcement assembly and ensuring a fully connected, accurately positioned BAMTech system ready for concreting. The process begins by positioning the steel bar on a manual bending machine designed for quick on-site work. The operator aligns the E5.0 mm rebar to the marked dimensions of 24 by 44 centimeters and locks it against the bending pin. Using the short lever arm, force is applied gradually to form each angle. To improve leverage, the arm is extended to about 80 centimeters. Each bend is checked for accuracy before moving to the next, ensuring consistent stirrup geometry. This manual method suits light rebar and avoids excessive machine stress damage. This system developed is a fully automatic solution designed for high-capacity production of lead and lead alloy ingots. The machine installed for a client in China operates at 20 tons per hour, producing 25 kilograms ingots, and converts molten lead from existing kettles into solid, neatly stacked products. The process is divided into two main units. First, an inline horizontal waterbed casting conveyor equipped with a double chain carries fixed molds through a cooling water tank. This controlled water cooling ensures rapid solidification while stamping each ingot, without generating steam or harmful vapors. Next, an automatic stacking machine checks ingot dimensions, groups rows of 5 ingots, and forms uniform stacks on a receiving conveyor where they are weighed and automatically strapped. The entire system is fully integrated with a central control system for monitoring, checking, and data recording, ensuring safe, efficient, and reliable operation. The dry cast machinery cover slab production process begins with preparing a low-slump concrete mix suitable for dry casting. Aggregates, cement, and carefully controlled moisture are blended to achieve a stiff consistency that can be compacted through vibration rather than flow. This mix is transferred directly to the production line, where pallets are positioned beneath the forming equipment. Concrete is discharged onto the pallet and distributed evenly into the mold that defines the large diameter cover slab used for manhole rings. The Coot rotoscreed mixer ensures uniform material distribution and consistent mix quality before compaction. Once the mold is filled, the pallet moves onto the Coot vibrating table. Here, powerful and precisely controlled vibration compacts the dry concrete, forcing it tightly into every detail of the mold. This vibration process eliminates air voids, increases density, and produces a smooth, high-quality surface finish despite the low water content. After vibration, the slab retains its shape immediately, allowing the mold to be lifted without deformation. The green product remains on the pallet and is transferred using the Coot pallet lifting system. This system is equipped with an integrated clamping and unloading mechanism, which securely grips the pallet and safely moves the freshly formed cover slab to the next stage without damaging edges or surfaces. The slabs are then placed in a controlled curing area, where strength develops through hydration under carefully managed conditions. Because the dry cast method produces dense concrete with minimal excess water, curing times are efficient and dimensional accuracy is maintained. Once sufficient strength is achieved, the slabs are demolded completely, inspected, and prepared for storage or dispatch. Throughout the process, the combination of the Coot rotoscreed mixer, high-performance vibrating table, and automated pallet handling ensures repeatable production and excellent surface quality. This integrated dry cast system allows the efficient manufacture of large-diameter machinery cover slabs that meet demanding structural and durability requirements for precast concrete manhole applications.